Okay, let's go ahead and get started. Um, are- any questions on anything up to this point? Just let me know. It was wrong, even though you watched the video. It shows to help. It was the same answer, but it's still saying wrong. Did anyone else have that problem on number 6B? So was that a domain issue? Yeah, okay. So what was the you had to put it in interval notation. So okay. Okay, so yeah, let's take a look at it. Do you have it up? Can you bring it up, the problem on your screen? Victor or Achilles? The Celsius problem? Okay. Maybe, yeah, maybe there's, oh, was it the Celsius problem? No. Yeah, I don't know, because I mean there were some people that got 11s out of 11, so so yeah, let's see what we got here. Or maybe that was just maybe that was 6.1. Are we talking about 6.1 or 6.2? It was 6.1, right? Yeah, 6.1. Okay, so um, if you can bring it up and share your screen, that'd be great. So is it asking? It's just asking for, well, if it's the Celsius to Fahrenheit, right? Um, what did you get for your domain? Did you put did you put negative infinity to infinity, or did you put the restrictions that okay? So negative 273.15 to infinity. This is the answer that was marked as correct. Yeah, exactly. So they give you restrictions on your domain in the problem. Thank you, Alexis. Does that make sense? And if you read the problem carefully, they tell you that there's a restriction on the domain for your temperature, and then you have to convert that. Okay? Okay. So hopefully that answers the question. Oh, interval notation. Yeah, interval notation. Okay. Okay, let's go ahead and get into today's lecture then. Okay. Let me share my screen. Okay. Okay, 6.3 is the natural exponential function. Cancel. Okay, so the natural exponential function, natural exponents. So 6.3 star, okay, is natural exponential function. So what do I want to write in today? So natural exponential function. Okay, and a couple things that we need to note is that for the natural exponential function, right, the natural exponent, that would be y equals e to the x. That's going to look like this, right? Okay, so a couple of things. So the limit as x goes to negative infinity of e to the x is equal to 0. So that's approaching 0 from as I go to negative infinity. It's approaching 0. Okay, the limit of that thing is 0. And then the limit as x goes to positive infinity of e to the x is infinity, right? Positive infinity. So just a couple of things to note about the shape and behavior of the natural exponential function. Okay, so then I'll underline that. Okay, number 1. Okay, find the limit as x goes to infinity of e to the 2x over e to the 2x plus 1. Okay, e to the 2x plus 1. So what I'm going to do is I'm going to take this, I'm going to divide both top and bottom by e to the 2x. Okay. And what that's going to give me is this is now going to give me the limit as x goes to infinity of 1 over 1 plus 1 over e to the 2x. Okay, well, this thing is going to go to 0, right? Because it's basically 1 over infinity, right? So if e to the x goes to infinity, then e to the 2x goes to infinity. And 1 over infinity is 0. The limit of as 1 over that function, okay, is going to approach 0. Okay, and so this limit is just equal to 1. Okay, for that limit. Okay. Okay, number 2. Actually, not number 2. Let's do a proof. Let's do a proof of the fact that d dx of e to the x is equal to e to the x. Okay, so the derivative of e to the x is itself. That's a very special nature of the natural exponent, is that it is its own derivative. Okay, it is its own derivative. Now let's prove this. Okay, proof. Okay, let's do a proof of this. So I'm going to take y equals e to the x. Okay, and then I'm going to take the natural log of both sides. Natural log y equals the natural log of e to the x. And then I'm going to differentiate with respect to x both sides. Okay. Okay, so d dx natural log y, well, that's just going to be y. It's going to be 1 over y, right? Natural log of y, the derivative of natural log y is 1 over y times y prime. Why? Because y is a function of x. Y is a function of x. So we're doing implicit differentiation. What's the natural log e to the x? Well, that's just x. These two functions are inverses of each other. They undo each other. And so that's just x. Okay, so d dx of x, right? Okay, so we've got y prime over y is equal to, okay, d dx over x, which, well, what's the derivative of x? It's just 1, right? It's just 1. Okay, so then this tells me that y prime was equal to y. That's interesting, that the derivative is the original function. Y prime was equal to e to the x. Oh, okay. So we started with y equaling e to the x, and we ended up with y prime equals e to the x, and so we showed that d dx of e to the x is equal to e to the x, and I'm going to put a little box there, okay? Okay, that little box means QED, QED, okay? And that QED actually stands for quid erat demonstratum, demonstrandum. Okay, quid, it's Latin. Quid erat demonstratum, and it means that it has been demonstrated. Okay, what was to be shown has been shown. Okay, and that's just means we've proven what we wanted to prove. We proved what? We proved the statement here. Okay, so that's what this little triangle means, or this little square means. It means that Latin, it has been proven. We have proven that mathematically beyond a shadow of a doubt. We know that this is true. It will always be true from now until the end of time. Okay. Okay, let's go away. Okay, let's talk about the derivative of e to the u. Okay, e to the u. Okay, e to the u of x. Okay, we're going to use the chain rule on this one, right? So this is going to be the derivative of e to the u is, well, e to the u, but it's then the derivative of u, right? It's the derivative of u, or u prime. Okay, so if it's a function that is the exponent, then we just multiply by u prime there. Okay, so that's by the chain rule. It's a more formal definition of this. Okay, let's utilize this to do a problem, shall we? Okay, number 2. Okay, number 2 is find y prime if, okay, if y is equal to e to the negative 4x sine 5x. Okay, e to the negative 4x sine 5x. Okay, so what are we going to do here? Any ideas? What rule are we going to use here?
Is it product rule?
Yeah, absolutely. Who is that?
Sierra.
Sierra, thank you, Sarah. Yeah, absolutely, Sarah. It is the product rule. We are going to use the product rule here. We've got a function times another function, and we're going to use product rule. So y prime equals derivative of the first. Well, derivative of the first, that's going to be e to the negative 4x times the derivative of 4x, which is negative 4, right? Times the sine of 5x plus, okay, we're going to keep the first and then take the derivative of the second. So the first is just going to be e to the negative 4x. The derivative of sine, I know, is cosine, right? So that's cosine of 5x times the derivative inside, which is 5. Right? Okay. So I'm going to factor out what they have in common here. Well, they have the e to the negative 4x in common. So we've got e to the negative 4x times, I'm going to put the positive term first, just because I like to stay positive. I'm a very positive person. Let's keep things positive if we can. Okay, so 5 times the cosine of 5x minus 4 times the sine of 5x, right? Okay, and that's e to the negative 4, so I think we're good on that one. It's good. Nice. Okay. Okay, any question on anything we've done so far? Okay, let me know. Okay, number 3. Number 3, find the first and second derivatives. Okay, find f prime of x and f double prime of x of e to the 1 over x. Y equals, or sorry, f of x, I should put f of x. Keep the notation the same. F of x equals 1, oh, sorry. e to the 1 over x. Okay, e to the 1 over x. Okay, so let's take the first derivative here. Okay, f prime of x. Derivative of the first, our derivative of the e is itself, right? Derivative of e is itself, e to the x, times the derivative of 1 over x. Well, what's the derivative of 1 over x? Well, 1 over x is the same as x to the negative first power, right? So that would be negative 1 over x squared. Okay, or negative x to the negative, negative x to the negative second power. Okay, you could think of this is going to become, right, negative 1 times x to the negative second power. Does that make sense? Oh, there's a 1 over x here. Thank you. Okay. Yeah, typo. Yep. Okay. No, thank you. Okay, and then this is going to become, okay, negative e to the 1 over x all over x squared. Okay, so that's the first derivative there. Okay, so first derivative is that one. Okay, the second derivative, okay, I'm going to look at this guy here. It's going to be product rule again, right? So that's going to be product rule. So we have e, the derivative of the first. Well, we already know what that is, right? We just got that. That's right here. That's negative e to the negative 1 over x squared. So I'm going to cheat. I'm going to write that. So this is going to be derivative of the first, which is negative 1 e, oops, negative e to the 1 over x squared times negative 1 over x squared, okay, plus, right, plus, what do we got? The first times the derivative of the second, so this is e to the 1 over x, okay, times the derivative of negative x to the negative 2. Well, that's going to be positive, right? So this thing here, there's a negative here, by the way. Just don't want to make sure that negative gets lost. So if I look at this guy here, this is negative x to the negative 2, right? So if I bring the negative 2 down, that becomes a positive 2x to the negative third power, right? So this is going to be times 2 over x cubed, right? Okay. So then let's simplify this guy. This is going to become e to the 1 over x all over x to the fourth plus 2e to the 1 over x all over x cubed. Okay, nice. Okay, and so I'm going to create a common denominator here by multiplying both top and bottom by x. And then I'm going to factor out what they have in common. Okay, so well, let's create the common denominator first. This is going to be e to the 1 over x plus 2x e to the 1 over x all over x to the fourth, right? And now I'm going to factor out what they have in common. Okay, so what do they have in common here? Well, they have in common a e to the 1 over x. I'm going to pull that x to the fourth out in front as well. And then when I factor all that out, I'm left with 1 plus 2x. And you can rewrite that as 2x plus 1 if you really wanted to. You know, if you wanted to keep it in descending order of power, you can go ahead and do that. But at that point, I'm done. Okay. Okay. Let's talk about this guy here. Let's talk about what's the integral of e to the x dx? Anybody know? What's the integral of e to the x dx? Say it again.
E to the x.
Okay, e to the x? Is that what you're saying?
Yeah.
Okay,
Yeah.
e to the x plus c.
Plus C.
Always plus c.
Yeah,
Okay.
sorry.
Always plus c. Always plus c. Okay, e to the x plus c, right? E to the x plus c. So the integral of e to the x is equal to e to the x plus c. Okay, exactly. Thank you, Raj, for doing that, and thank you, Anthony, for laughing at my jokes. I appreciate that. It doesn't help you in the class to laugh at my jokes, but it can't hurt you. Just keep that in mind. Okay. So I do appreciate the pity laughs. They go a long way to boost my self-esteem. Okay, evaluate. Let's do this here. Evaluate. Okay, let's evaluate number 4 here. Okay. 0 to 1 of x squared e to the x cubed dx. Okay, u sub on this, right? Okay, or we could do integration by parts, but you guys don't know that yet. Okay, which don't do that. This is a u sub. Okay, so what's going to be my u in this case? What's going to be u?
X to the power of 3.
Yes, absolutely. Thank you. X to the third power is going to be, okay, thank you. Was that Fady?
Yeah.
Thank you, Fady. Yeah, x to the third power. Why do I want that to be my u sub? Because when I take the derivative of a cubic, don't I get a squared? Does it make sense? It's going to drop by a power, right? Okay, so it's going to drop a power, and so we're going to get du is equal to 3x squared dx, right? And then, well, I have the x squared, and I have the dx, but I don't have the 3. So I'm going to divide by 3, and I get the du over 3 is equal to x squared dx. Okay, so now I can do my u sub. Well, sort of. Let's look at our limits of integration. What's u evaluated for 1? What's u evaluated for 1? Well, isn't that just going to be 1 cubed, which is 1? Does that make sense? U evaluated for 1. If I plug 1 in there, don't I get 1 back out? Right? Okay, what about u of 0? What's u of 0? What's u of 0?
0.
0. Thank you, Sierra. Okay, u of 0 is 0. Okay, so 0, boom. Okay, so what are my limits of integration going to be then? Well, they're going to be exactly the same thing. That's kind of convenient. It's nice and convenient. 0 to 1, okay, of, okay, e to the u du over 3. Okay, d over 3. Right?
So, sorry, I have a question.
Yeah, go ahead.
So when we're doing the u substitution, what we're
Yes.
trying to get is to get the other variable, like the x squared on the side of the dx, so that we can cancel it out and just do du over 3 or du over whatever.
Yeah, we're substituting, right? When we say u substitute, right? We're substituting for the x cubed, but then when we take the derivative with respect to x, we're then substituting that for our derivative. We're substituting du over 3 for this value x squared and the derivative dx.
Okay.
Okay,
Thank
so
you.
we're piecing it together, right? We kind of like want to take the pieces that we know and the pieces that we want, and we want to swap them out. Okay. Okay, and so we get EU. Okay, so I'm going to pull that 1/3 out in front. 0 to 1 EU du. But what did we say was the integral of e to the u? Wasn't it just e to the u? Right? Isn't the integral of e to the u e to the u? Well, sure. E to the x is e to the x. E to the u is e to the u. Okay. So this is just going to be 1/3 e to the u evaluated from 0 to 1. Okay. Which is just going to be 1/3 e to the 1 minus 1/3 e to the 0. Okay, so I could factor out that 1/3 if I really wanted to. It doesn't matter. What's e to the 1? What's e to the 1? Any ideas? What's e to the 1? Isn't that just e? Right? It's just e. Okay, so this is e over 3 minus, what's e to the 0? Well, anything to the 0 is 1, right? So isn't that just 1/3? So wouldn't this just be e minus 1 over 3? Okay. And e is approximately what? Anybody know what e is approximately? Any ideas? What is e approximately? No? What did you get? Okay, no Googling. Don't cheat. Okay, Michael?
It's 2.718281828.
How did you know that?
Oh, I had my calculator.
Oh, geez, you cheater. Okay, it's 2.718281828. Sorry, 45, 90, 45. I believe. Is that right? Is that?
Professor, do I really need to do that? Like, or can I just leave it like e minus 1 over 3?
Yeah, you can leave it as e minus 1 over 3. Is this correct? Let me check with my calculator to see if this is correct. 1828, 1828, 45, 90, 45. I believe that's correct. Okay. So, okay, so you're right. Yeah, I have this memorized. It's really easy to remember this, actually. Isn't this? It's totally easy to remember this. Okay, because what you do is there's only been one president that's actually shot someone and killed them, and that was Andrew Jackson, the guy on the what is he on? Is he on the $20 bill? I think he's on the $20 bill. Okay, Andrew Jackson, he shot and killed a guy in a duel. And so the mnemonic device here goes Jackson, who was president in 1828. Jackson carried a pair of Colt 45s. Okay, Colt 45 was a pistol. Okay, if you didn't know that. Okay, Jackson carried a pair of Colt 45s until he was 90 when he died. Until he was 90. Boom. And that's how we remember. Okay, E to what is this, 13 digits? Okay, so E to 13 digits, real easy to remember. Jackson carried a pair of Colt 45s until he was 90. 2.7, 1828, 1828, 1828, 1828, 45, 90, 45. So a little mnemonic device that you may not have been aware of. Okay, pass along to your friends and neighbors. Okay, you can tell that to your parents tonight. Hey, guess what I learned? I learned that Andrew Jackson on the $20 bill, he shot some guy in a duel to defending his wife's honor, and he got shot too. He just didn't die. The other guy died. They both shot each other. And this was legal back in 1828. So I'm glad that we've evolved as a species a little more beyond the whole shooting people after dinner. So, but who knows, you know? Right? Okay. Yeah. Okay, Jackson, right? Okay, so if you wanted to do an approximation of this, you could do an approximation of this if you wanted to, and that would be 0.5728. Okay, either of those is correct. Okay, going back to Fadi's question. Okay, one is symbolically correct and one's numerically correct, and this just goes on forever because it's transcendental. Okay. Okay, any questions so far? Are we doing good? Doing good? Okay. Let me check something real quick. Okay, perfect. Okay, so that's 6.3 in a nutshell. Let's move on to 6.4. Man, that was quick. That only took us a half hour. Nice, that's good. Okay, let's move on to 6.4, shall we? Oh yes, we shall. We shall. So, okay, so again, I have couple, 6.4. Let's just jump right into that bad boy. Okay, 6.4. What is 6.4 all about? 6.4 star. It is general, okay, logarithmic I can't even spell. Okay, general logarithmic. Okay, functions
Are you
here.
gonna pick up your stuff, please?
Say that again.
I'm gonna clean up your stuff.
Okay, I'll try to clean up my desk. Sorry. Let me Oh yeah, if you could mute yourself, that'd be great. Okay, so I don't really have generally a messy desk, so it's all good. Okay. Okay, general logarithmic and exponential functions. Okay, so general logarithmic and exponential functions. You're like, well, you know, what are general logarithmic and exponential functions? Well, they look like this, right? Okay, but we're more interested. This is, you know, the general y equals a to the x. Okay, where we have a base. That's not e. It's a represents a constant here. Okay, it's like y equals 2 to the x, right? 2 to the, that's a general logarithmic, or sorry, general exponential function, right? So what about a general logarithmic function? Well, what if we had something that looked like this, right? And so we said that this was y equals log base 2 of x, right? That's a general logarithmic function and general exponential function. So let's take the derivatives of the general exponential first. Okay, the general exponential. Let's do a ddx of this guy. Okay. Okay, ddx of b to the x, okay, is equal to b to the x natural log of b. Okay, that's what that thing becomes. Okay, when I take, now the derivative of e to the x was e to the x, so that one's easy. But this one is b to the x equals b to the x natural log b, where b is a constant, and b cannot, basically b has to be greater than 1. Okay, it has to be a number greater than 1. So b is greater than 1. Okay. So we have a domain issue there. We don't want it to be negative, because then it oscillates back and forth and it doesn't create a nice function. And it's just not, that's not a real valued function. And we don't want it to be 0, because then it just wipes everything out. Okay, we can't even take the natural log. So we end up with basically 0 times infinity, which is just, it's not fun. Okay, so we're just going to restrict our domain on what b can be to greater than 1. Okay, so let's do a proof of this. Again, ooh, proofs. Yes, proofs are fun. Why are proofs fun? Because we prove why something works. And the why something works is so much more important than the how it works. So let's prove this thing to be true. Okay. Okay. Although I couldn't convince my daughter, who just finished geometry, that proofs were cool. She still doesn't believe it. She's like, no, Dad, they're not cool. They're never cool. They will never be cool. And she has no idea what I'm talking about. She does not like math at all. She despises math. I think that was God's little ironic humor, was to give me a daughter who hates math with a passion. So that was, yeah, that was fun times in the Holtman household. Exactly. Thank you, Susan. Yeah. So if I have a picture, I'll show you a picture later on of what she drew when she was in 2nd grade. It was really sad. She basically drew herself at a desk, little stick figure here, person at a desk. And she had a piece of paper here, 2nd grade, and she said there's an F on the paper, and she says she said, she had long hair at the time, so she said, I gave myself an F because math is too hard. Yeah, so it broke my heart. He says, I gave myself an F because math is too hard. She wasn't smiling, by the way. Now she's decapitated. That's not good. Okay, so she was crying. She had little tears, crying, and it was so sad. And my heart broke for her. And I said, no, math is not hard. Okay, you just have awful teachers. No, I'm just kidding. Okay, don't blame the teacher. Don't ever do that. Okay, so yeah, so anyway, math is not hard, and she's still not convinced that math is not hard. She's an artist, and she sells her art already at 15 years old. So, so she can say, you know, we're all talented in our own way, right? So anyway, thank you for letting me digress. Okay, I have stories to tell. Yeah, exactly. There we go. Okay, so let's prove this. Let's prove this, right? Prove d dx of b to the x is equal to b to the x natural log b. Okay, b is greater than 1. Let's go to our proof. Okay, math is not hard. It's easy. Okay, when you know the rules, all you got to do is follow the rules. Okay, just follow the rules. Math is a piece of cake, right? So just follow the rules. Okay, so let's see whether the rules are here. Let's go y equals b to the x, right? Y equals b to the x. Okay, let's do our logarithmic differentiation. Let's take natural log of both sides, logarithmic differentiation. Okay, so natural log of both sides. Nice, nice, nice. Okay, and then we're gonna do what? Well, let's drop this x in front. Let's use the properties of logs to drop that x in front. So we're gonna take the natural log of y is equal to x times the natural log of b. Do you have a question? Okay. Did you E or B or Ebony? Did you have a question? No? Okay, just let me know. Okay, so we're doing it for the general form this time, right? Oh, accident. Okay, that's fine. Okay, natural log of y is equal to x natural log of b, right? And then what are we gonna do? We're gonna take the derivative of both of these. Okay, both sides. Take the derivative of both sides. Okay, and we're gonna get again y prime over y. I've done this already a bunch, so I'm just going to go y prime over y is equal to, what's this going to be? Well, what is natural log b? Isn't natural log b just a constant? Isn't just this a number? It's just a number, it's just a value. So isn't that just going to be natural log b? Right? Because isn't this just like, what's the derivative of 3x? Well, the derivative of 3x is 3. So what's the derivative of natural log b? X. Well, isn't it just natural log b? Does that make sense? Okay, so yeah, so that's just natural log b. So then we're going to get y prime equals y times natural log b. But what was y? Well, y prime was equal to b to the x natural log b. Boom, that's it. Easy. Nice. Okay. Okay, let's do a problem with this. Okay, let's do a problem with this. Number 1. Okay, d dx of 10 to the x to the second. Ooh, we've got powers on powers, baby. Woohoo. Okay, we've got powers of powers. Okay. Okay, so d dx of 10 to the x squared. Well, let's take the derivative of this, right? So the base is 10, right? So this is just going to be, it's an exponential. So the first thing is just to say, well, what's the original function? The original function is 10 to the x squared. So that's 10 to the x squared. And then I want to, right, do the natural log, okay, of, right, of the natural log of b. Okay, well, what's b in this case? B is going to be 10. Okay, except for what? Except for, well, we don't just have an x, we have an x squared, right? And so we have to use the chain rule because it's a function. The exponent is a function. So this tells me chain rule. Okay, chain rule. Okay, so how are we going to apply the chain rule here? Well, instead of it being just x, right, it's 10 to the x, so it would be 10 to the x log, natural log 10, it's 10 to the x squared, and so we have to take the derivative of x squared. And when we take the derivative of x squared, we get 2x. And so we have to take the chain rule there. And so this thing becomes, at the very end, okay, this thing becomes 2 times the natural log of 10. Why am I writing it like that? Because this is just a number, times x to the 10, x squared. Okay. But what is 2 natural log of 10? Well, that's going to be, I'm going to rewrite that as natural log of 100. Okay. Now, it may not be more simplified. Either way, I still have the same number of symbols. So, but I just kind of like it. I'm going to flex my logarithmic prowess here and just say, hey, you know what? I can make this thing squared and make that 10 squared. And so it's 100. And so we get x to the 10x squared. Okay, makes sense?
So if we just left the 2 in front,
Yeah,
like on a test or something,
that would be fine.
would it be okay?
Yeah.
Okay.
That'll be fine. Now, keep in mind that when you submit an answer, you're going to be submitting it in WebAssign. Okay, and you have 2 attempts. Okay, to submit it correctly. 2 attempts. That's it. Okay, you get 5 on the homework. You get 2 on the exam. Okay.
Wait. So then, how do we show our working?
Yeah. Okay. So let me show you how you show your work. So you'll be working out all the problems on paper, and then you're going to upload a PDF of all of your work. Okay, in Canvas in Proctorio. Okay, so it's a good question. Okay, so if I go to our class, let me go to our class. Okay.
So, sorry, I just have one more question.
No, go ahead.
Because we're doing all of the exams in WebAssign, like the problems on the WebAssign homework are probably most like what's going to be on the exam.
Yes,
Is that
correct?
right?
Yes.
Okay, thank you.
Yes, they're different but similar. Okay, and so then you would go to quizzes. Exams is quizzes. They're the same thing. Okay, you would go to quizzes or oh, look, it's even here right now. Chapter 6 exam, remotely proctored. I would go in here, and there's only one question on the quiz. So somehow we managed to not get it right onto 2 attempts, but the work we uploaded was right. Would it be counted as correct? Probably not. To answer Joseph's question. So probably not. So just to keep
But
that in mind.
sometimes the answer that's on the WebAssign will be more simplified somehow that more than the way that I roll my answer. So it will be considered wrong because the WebAssign is just like has one answer that it should match my answer. Like if, for example, if I roll two natural log 10 times or
Right.
to the x power 10 to the x power 2. And the WebAssign I should write natural log of 100 or whatever what is written on the WebAssign. So
well, WebAssign's smart enough to figure that out.
Yeah, he will figure the WebAssign will figure it out. That's what
you know. But if you miss a negative sign or you do something like that, then yeah, there is already partial credit added into the equation. So answering Victor's question. So just to let you know. Okay. So you get credit based on your answers, and you get credit based on your work. Does that make sense?
Got it. Thank you.
So yeah. Okay. So if you go in here and say exam 6 remotely proctored. Okay.
So we can't see the screen.
Oh, you can't see my screen?
No.
Oh yes, sorry, my bad. Okay. Sorry. Let me share my screen, not my others. Can you see it now?
Yes.
Can you hear me now? Yeah, no. That's an old
Yeah,
one.
we can see.
Oh, okay, good.
Oh.
Okay. Can you see me now? What about now? Can you see me now? Yeah, okay.
Yes.
Yes. Okay, good. Thank you, Michael. Okay. So anyway, that's the old Verizon commercial. Can you hear me now? Okay, forget it. If you have to explain a joke, it's a dead joke, right? It's like if you have to explain a meme, it's a dead meme, right? That's just the way it goes. Okay, so so you will go in here, right? And it says it's a graded quiz. Okay, available. I'm going to hit preview on this, and then it says what? It says that you have I don't know. Maybe I have to be in student view. Anyway, it'll ask you to upload your PDF file, okay? And then you submit it here. Okay, so hopefully that makes sense. But again, as the exam gets closer, we'll go over more and more in this. But I think I do have to, oh no, here it is. Okay, question 1 right there, boom. Okay, it's gonna ask you for your PDF. Okay, it's unanswered, blah, blah, blah. Okay, so, right, so, okay, you have 180 minutes to do it. Okay, unanswered, and it says, you know, oh, this is for me. This is for me to grade. I'm in the grading thing. Yeah, I have to be in the student view, but anyway, it asks you for, if I go into edit it, I'll show you real quick. Let me get out of this. Where is it? Go home. Let's go to home, and anyway, there's a place for you to upload your file. Let me say no. No, I do not want the gradebook. Get out of the gradebook. Okay, get out of the gradebook. Go away. Anyway, I'm gonna stop my video. Okay. Home. Home. Go home. Okay. There we go. Okay. So if I go to the assignments, okay, and it should say, okay, it's not available until the exam day, which is next week. Okay, which is actually a week from today. Woohoo, aren't you guys lucky? Your first exam is 1 week from today. Okay, so if I go into edit here, okay, more options. Okay, and it says, okay, the questions, right? So it's remotely proctored by Proctorio, and the question says, okay, it says right here, please upload a PDF of your original work in sequential order for Chapter 6 exam. Okay, and you would upload, okay, you would upload for this guy here. Okay, so you would click on that, and then you would upload your work. Okay. Okay, so boom, save. Okay. Okay. So that's that right there. So hopefully that answers some of the questions. How many questions are on the exam? I don't know. 150? Does it really matter? It's like asking, are we there yet? In a card, right? Does it like 15 hours until we get there? That's what I used to tell my kids. 15 hours? And then they'd be like, I'm said within plus or minus 15 hours. So let me give you a range. Plus or minus 30. So how's that? Okay, 30 plus or minus 30. As little as 0, as many as 60. So there we go. Okay. Okay, let's do number 2. I probably shouldn't say it like that. That's probably bad. Let's work on problem number 2, shall we? Oh yes, we shall. Okay, first, let's do. Let's look at the integral of b to the x. What's the integral of b to the x dx? Well, I'm glad you asked. It's b to the x over the natural log of b plus c, where b is greater than 1. Things that make you go, right? Why is that the integral of b to the x? Well, what was the derivative of b to the x? Wasn't the derivative of b to the x equal to b to the x, whoops, this is a b to the x, sorry. B to the x natural log of b, but isn't natural log of b just a constant? Isn't natural log of b just a constant? So couldn't I just divide by natural, let's just divide by natural log of b. Right, and so what do we get? We get d dx of b to the x over natural log b is equal to b to the x, right? Okay, nice, yeah. So let's take the integral of both sides, right, with respect to x. Ooh, and what's the integral of the derivative? Well, don't those cancel each other out? And so wouldn't this be b to the x over natural log b plus c? I think so. Oh, that's pretty cool. It's pretty snazzy, pretty slick, as my grandparents used to say. That was the something generation. That was the greatest generation. They were called the greatest generation. I don't know why they were called the greatest generation. The greatest generation, which who knows? Okay, so they're like, that's sure slick. Like, thanks, Gramps. Now it's, you know, okay, boomer, right? Like, basically, it's my parents' generation. Okay. Okay, let's do some integration. Okay. Yeah, so we have what? We have the boomers now that are still alive. If you're the greatest generation, man, that's okay. You're like 100 or something, right? So you're pushing the envelope if you're greatest generation. If you're a boomer, you're like probably in your 70s, 60s, 70s. Okay. Generation X, right? 40s, 50s, right? Generation X, 40s, 50s, and then there's millennials, right? That's 20s, 30s right now. And then Generation Z, which is basically 0 to 20, I think, right now. So those are the generations. So it's interesting. Okay. Anyway, it's not part of the class. So let's move on to the calculus. Okay. So let's integrate 0 to 5 of 2 to the x dx. 2 to the x dx. Okay, 0 to 5, 2 to the x dx. Okay. Okay, and so what's this going to become? Well, this is going to be 2 to the x dx. So that was, the integral was 2 to the x over natural log of 2, right? Evaluated from 0 to 5. Oh, okay. Oh, we're on number 3? You sure? I don't think, I think we did a proof, right? Did we do a proof? No, we're not number 2. So, yeah, oh, sorry, this was a proof. This was a proof. I think I called that number 2, but it shouldn't have. So this is the true 2. Okay, true 2. Thanks. Okay, so we've got 2 to the 5th power, okay, over natural log 2, minus 2 to the 0 power over natural log 2. And this is going to be equal to 32 over natural log 2 minus 1 over natural log 2, which is 31 over natural log 2. So, nice. Nice example there. Okay. So it's interesting. I have 2 teachers in here, two math teachers. Is it Sandra? It's Ebony and Sandra, I think. Is it Sandra? Yes?
It's Susan.
Oh, Susan. Sorry. Okay, I'll get that right. Thank you.
Yeah.
So Susan.
No problem.
No, okay. So I've got Susan and Ebony. Any other math teachers in here? So, and I got a lot of UC students as well. A lot of Berkeley people. Go Cal, right? So go Bears. My grandfather actually, he graduated from Berkeley. So as a pharmacist, he owned his own drugstore. So that was kind of cool. So yeah, go Bears, exactly. So nice. Yeah, a lot of Berkeley people in here. So so yeah, so that's kind of cool. I don't know where I was going with that, but anyway. Oh, teachers. We got a lot of teachers in here, right? So when a little story to digress for a second. Go Bruins. That's cool. Okay, Cal is slick. Nice. There you go. Okay, so so when I started teaching, these are just for the teachers. Okay, so this is my 20 years of wisdom in one sentence, basically, on teaching. Okay, when I started teaching, and I was like, oh yeah, I'm going to teach. That's awesome, right? So I started teaching, and then I taught middle school for 1 year, hated it, absolutely hated it. And then I was like, I'm out of here. I'm done with the middle school. So then I heard that the calculus teacher was retiring from teaching calculus to high school. So then I was like, oh, I want that job. So then I transferred to the high school the next year, and then I got that job. I got the teaching calculus at the high school level the next year. So after 1 year of teaching, I moved up, and after 2 years of teaching, I was teaching calculus BC at the time. And then the next year I was teaching, and I was teaching, I think it was like algebra like 1 or something like that. And I came home to my wife and I said, I'm quitting. I'm never teaching again for the rest of my life. Right? So never teaching again. I'm done. After 3 years, it was 3 and done. So 3 years, I'm done. I'm going to do engineering. I'm going to do something else with my degree, blah, blah, blah. I'm done. I'm never stepping foot into another classroom for the rest of my life. And she turned to me and she says, well, okay, fine. I'll support whatever you decide. However, yeah, I'd really like to know why you don't want to teach anymore. And I said, because these kids are so incredibly stupid. I was like, I don't know how they tie their shoes in the morning. Like, I just don't get it. Right? And so, I know, right? Like, they have very poor kids. They're just sad. It was a sad state of affairs. Okay. It was sad. I was like, they're just dumb as rocks. And I cannot teach these people that just cannot do anything. I like tell them, put your pencil in your hand and please put the pencil to the paper and let's do some math. And that was every single day. I could just tape record myself. Could you pick up your pencil now? Could you pick up your pencil now? Could you please pick up your pencil again? Yes, let's do some math. And I came home and I was burnt. I was like, forget it. I'm done. I never want to do this again for the rest of my life. And she turned to me and she said, yeah, well, you probably shouldn't teach because you're not geared for this teaching thing. Why would you ever step foot in a classroom if you had that attitude? And I'm like, what are you talking about? And she turned to me and she said, Jason, she says, all your life you've been looking to be first. You graduated from high school with honors. You graduated from college with honors. You graduated from grad school with honors. They gave me a frickin' medal when I walked across that podium. A medal, like I have like the medal. And she said, you've been climbing this mountain of mathematics for the last 14 years of studying math. And she says, you don't get it, do you? And I'm like, what do you mean? She said, this is not about you. She said, you've climbed this mountain and you're at the top looking down at all these quote unquote stupid kids who can't do anything that you can do. Of course they can't do anything you can do because you're at the top of the mountain looking down, and it's very lonely up there at the top, isn't it? And I said, okay, well, what's your point? And she said, your job as a teacher is not to be on top of the mountain. It's to get everyone else there with you. And that was 17 years ago. And that one statement changed my entire perspective. At that point in time, I didn't teach math anymore. I taught people. And I taught students. And it wasn't about me getting across the finish line first anymore. It was how many people can I get across that finish line with me? And so that is for the teachers in the room here. That is from 20 years of doing this job and putting that into practice on a daily basis. So anyway, I thought I would I would share. Okay, I don't know. It's like, oh my gosh, it's getting deep. It's getting okay. Sorry. Anyway, I just thought I would let you know. She was right. Exactly. That's why I'm still married to her. Bam. You know, found a good one. Anyway. Okay. Let's get back into the math here, the mathiness. Okay. Okay, let's differentiate number 3. Now it's number 3. Okay, let's differentiate y equals x to the square root of x. Okay, y equals x squared of x. Okay, put my video back on. Hopefully my internet doesn't lag anymore. It took me 3 weeks, and I finally got the guy out today to get me my internet boosted. I'm now at 600 MPS, whatever that means. No, I'm just kidding. It's megabytes per second. So it's 600. So it better not lag on me anymore like yesterday. Okay. So y equals x to the radical x. This is kind of interesting. Y equals x to the radical x. Okay, so let's find the derivative of this one. Find y prime. Okay, so we get y equals x to the 1/2 power. Okay, and so I'm going to use logarithmic differentiation on this. Okay, let's take the natural log of both sides. We're going to get natural log y equals, I'm going to bring this guy down, put him in front, x to the 1/2 natural log x. Okay. Okay, and so now we're going to get the derivative of both sides. Let's take the derivative of both sides. Okay, take the derivative of both sides there. There. Okay. Okay, and so this is going to be y prime over y. We've done that many times. Okay, and this is going to be what? Product rule, right? Product rule. Okay, so x to the 1/2, that's going to be 1/2 x to the negative 1/2 times the natural log of x, plus x to the 1/2 times 1 over x. Derivative of the first times the second, plus the first times the derivative of the second. Okay. Okay, let's clean this up a little bit. So we've got y prime over y is equal to, I'm going to go 1 over 2 x to the 1/2. That's 2 radical x, I believe. Natural log of x. Plus, this is going to be radical x over x. Right? But radical x over x, isn't that just 1 over radical x? Doesn't that just become 1 over radical x? Right? So, yeah, so we could get, this is 1 over 2 radical x times the natural log of x plus 1 over radical x. Okay, I want a common denominator if I can get one. I don't have a 2 here, so I'm just going to put a 2 there and a 2 there. And so I get natural log of x plus 2 all over 2 radical x, right? Okay, that's an ln, by the way, ln of x. Okay, plus 2 over 2 radical x. And then this is all times y, right? If we do the y. Okay, y because I asked, that's why. No, just kidding. Okay, so y, ln x plus 2, 2 radical x, y. What was y? What was our original function? Well, wasn't it just, it was the natural log of x raised to x, sorry, it was the, yeah, what was, sorry, y was equal to x to the radical x. So it was x to the radical x times the natural log of x plus 2 all over 2 radical x. And that's the derivative of that one. Cool. Nice. Nicely done. Okay, let's look at another property of logs here. If I wanted to take the derivative of a log base b, something that's other than base, okay, log base b, okay, this is going to be equal to 1 over x natural log, okay, natural log of b. Okay, and now let's do the proof of this. Let's prove this proof. Okay, let's proof this. Okay, log base b of x, log base b of x, okay, is equal to, okay, I'm going to use my change of base formula, right? Change of base, not to be confused with the 90s band Ace of Base. Sorry. Okay, so is the natural log of x over the natural log of b, right? So does that make sense? Natural log x, okay, that comes to us from the log base b of a equaling log of any base c of a over log of any base c of b. Okay, that's called the change of base formula. We're changing bases. Okay, I'm just using log base e, which is the natural log, as the base that I'm going to be using, right? So just change it to natural log. Why natural log? Because we already have rules for natural log. Why would I want to not use rules that I already have, right? Okay, so now let's take the derivative of both sides. d dx. Okay, d dx. Okay, this is going to be the derivative of log base b of x. What's the derivative of natural log of x? What's the derivative of natural log of x? Very good. Thank you, Sierra. Thank you, Anthony. Okay, awesome. Yes, it is 1 over x. Okay, so we have 1 over x, right? And then what's 1 over natural log of b? Isn't that just a constant? Isn't that just a constant? So it's, if I take the derivative of a constant times a function, isn't it just the constant is out in front? So wouldn't this just be equal to 1 over x natural log of b? Does that make sense? Okay. Again, showing why things work. You know, I could have you memorize this formula if you really want to, but what happens if you forget the formula? Then you're screwed, right? You're like, I forgot the formula. Now I have to look it up on Google, or I have to, you know, look it up in a book. Well, or you could just sit here and derive it. Again, it's real simple. If you understand these, you know, properties, then you can say, well, I could just rederive it, right? Oh, thank you. I think I rewrote it, but yeah. Thanks. Okay. So let's, and then I'll put a little square there. Okay. Don't forget our quid erat demonstrandum. Okay. Number 4. What's number 4 here? I can't even speak today. Differentiate. Okay. Differentiate. Okay. Differentiate. Okay. Y equals log base 10 of 2 plus sine x. Okay, log base 10 of 2 plus sine x. Okay, so again, this is a chain rule because we've got log base 10. Okay, so y prime is going to be what? It's going to be 1 over x natural log of b. Okay, so well, what's the x in this case? Well, the x is the 2 plus sine x, right? So think of this as, you know, if I wanted to look at, instead of log base b of u of x, right? So d dx, then wouldn't that be a chain rule? Okay, so what would this be? This would be 1 over u of x, okay, natural log of b times u prime of x. Does that make sense? So if we did a chain rule on that one, and this is what it would have to be. So let's do that for this guy here. This is going to be, okay, y prime is equal to 1 over, what's u of x? Well, it's the 2 plus sine x, okay, times the natural log of 10, okay, times u prime. Well, what's u prime? Well, that's cosine x. Right? So this thing's going to be equal to cosine x over 2 plus sine x times the natural log of 10. That's it. That's y prime. Okay. Easy, easy, easy. Okay. Nice. Okay, let's talk about the natural exponent. Okay. let's say that the number, okay, E, the number E, okay, Euler's number for E, okay, Euler's famous mathematician, okay, he was came after Newton by a few years, like maybe 30. E as a limit, the number E as a limit. Okay, let's look at the number E as a limit, the natural exponent as a limit. Okay, so let's write if f of x is equal to the natural log of x, then, okay, f prime of x is equal to what? 1 over x, yeah, exactly. Okay, as Sierra and I believe Anthony pointed out before. Okay, if we take ln of x, then the derivative is 1 over x, right? And f prime, okay, of 1 is equal to what? F prime of 1 is equal to, well, what's 1 over 1? It's just 1, right? Okay, from the definition, okay, oh, sorry, I should put a then, if then, from the definition of derivative, we have what? What's the definition of derivative? Definition of derivative is f prime of x, depends on which definition you're talking about. F of prime of x is the limit as h goes to 0, okay, of f of x plus h minus f of x all over h. Okay, so slope formula, as the points get closer and closer together, we're looking for the slope of the tangent line, right? So the limit of that value, slope of the tangent line. Okay, that's Calc 1 stuff. That's all hat for you guys, right? Okay, so hopefully you didn't forget that. Hopefully we're not measuring performance in college as much as we want to measure knowledge, right? So try not to get those two confused in college, right? You want knowledge over performance, okay? Right? Performance are going to get you a degree. Knowledge is going to get you a career, right? Just keep it balanced. Okay. If I handed out an A right now to everybody, that would serve absolutely nothing. Okay, because you would not be prepared for your career. That does you absolutely no good. Okay, there's a reason that your career of choice is requiring you to have this information. Okay, so f prime of x is equal to this, right? So what are we looking at though? We're looking at f of x being the natural log, right? So the natural log. Okay, so this is equal to the limit as h goes to 0 of the natural log of x plus h minus the natural log of x all over h. Okay. Okay. Let's look at f prime of 1. F prime of 1. Okay, f prime of 1 is the limit as h goes to 0 of, okay, what? We're going to replace 1 with x, okay, or we're going to replace x with 1. So this is the natural log of 1 plus h minus the natural log of 1 all over h. Okay, it's pretty cool. Pretty cool. Okay, but what did we say f prime of 1 already was? We already know the answer to this, right? What did we say f prime of 1 was? Well, f prime of 1 is equal to 1, right? It's equal to 1. So this guy's 1 is equal to the limit as h goes to 0 of, okay, the natural log of 1 plus h, okay, minus, well, what is the natural log of 1? Isn't the natural log of 1 0? Doesn't it go to 0? Right? So isn't this just the natural log of 1 plus h over h? Yep. Nice. Okay. Okay, so now I'm going to use, well, I don't want to skip steps here. I don't want to leave anyone behind. Okay? No toy gets left behind. Okay? Okay. So limit h goes to 0 of natural log of 1 plus h over h. Okay, and so, stop that. Stop. Behave. Okay, and so I'm going to rewrite this as the limit as h goes to 0 of 1 over h times the natural log of 1 plus h. And now I can use the property of logs by making this a power. So this is 1 equals the limit as h goes to 0 of the natural log of 1 plus h to the 1 over h. It's getting spicy. It's getting spicy. Okay, spice it up. Nice. Okay, so now I'm gonna do some cool stuff here. Okay, I'm gonna say that the limit of the log is the log of the limit. Ooh. Let me write that out because that is way too spicy. Okay, the limit of the log is the log of the limit. And you're like, what the heck does that mean? The limit of the log is the log of the limit. It just means this. It means that I can do this. Okay. Why can I do this? Because I am in charge. That's why. I'm just kidding. Okay, because limit laws, Calc 1. Okay, so the natural log of the limit of h goes to 0 of 1 plus h to the 1 over h, right, is equal to 1. That's pretty cool. Okay, so now how can I simplify this? Well, let's get rid of the natural log. I don't want the natural log. Let's raise this base e. Okay, let's make that base e. So e is equal to, okay, that cancels the limit of 1 plus h to the 1 over h, okay, as h goes to 0. Okay, so, okay, so now what I'm going to do is I'm going to spice some things up here. Okay, I want let h, well, let's see, let's let x equal 1 over h. Okay, let x equal 1 over h. Okay, so what is that? How can I change this by doing this substitution? Let x equal 1 over h? Okay. Okay, so then that means that h would be 1 over x. Does that make sense? This implies that h is 1 over x. Is that right? Yeah? Okay. Okay, okay. And the other thing that this implies is what? Is that the limit, right? The limit as h goes to 0, okay, the limit as h goes to 0 of 1 over h is equal to what? What is that equal to? If I take the limit as h goes to 0 of 1 over h, what does that equal to? What's 1 over h as h goes to 0? Anybody know?
1 over 0,
No?
which is undefined.
No, it's not 1 over 0. We're going to 0. We're not at 0. We never get there. Right? If I look at my graph of 1 over h, am I ever going to get to 0? No, I'm never going to get to 0. Why? Because it's an asymptote, right? Again, you don't want to make an asymptote out of yourself by thinking that it's a limit, right? This is a limit. So as h goes to 0, what does 1 over h go? Where is the function going? Fady? As
It might go to infinity.
absolutely, very good. Good job. As h goes to 0, the function goes to infinity, right? As h goes to 0, or x goes to 0, 1 over x goes to infinity, right? Does that make sense?
Yeah.
So the limit as h goes to 0 is the same as saying that, x goes to infinity. Okay, this x thing here is going to go to infinity. Does that make sense?
Yep.
Okay, so E is equal to the limit. I'm going to do the substitution here. The limit as x goes to infinity of 1 plus 1 over x to the x power. And that is the definition of the natural exponent as a limit. So this is the definition of the natural exponent as a limit. Does that make sense? Does that make sense what I did here? I mean, it should hold mathematically, right? Okay, that I'm using the definition of derivative, okay, to give me what the exponential function, the exponential base is, the natural exponent, as a function of a limit. Okay, now, why is this important? Why did we go through all of this? Except for the fact that it's beautiful math, right? Sometimes there's aesthetics in the math. Well, we didn't just do this for our health, okay? We did this because this is an extremely useful property. Is that E is what happens when we take the limit of this function, right? Right? As x goes to infinity of 1 plus 1 over x to the x, it's extremely useful. Does anybody know where we use this? Where do we use this property of E in real life? Anybody have any idea? No? It's okay if you don't. If you don't know, it's fine. I mean, that's why you're in this class, right? Okay, if you came with all the prerequisite knowledge, you would not need to take this class. Okay, well, there was a guy, okay, in 16, I don't know, 16, like, let me look it up. Maybe I'll look it up. I don't know, maybe I'll look it up on my phone instead of here because it's gonna lag if I use the internet on here. Okay, there's a guy, and I'm gonna, okay, and his name is Jacob Bernoulli. Jacob, and I always get his name wrong. I always get his name wrong. So let me make sure I don't. The Bernoullis were an extremely wealthy and powerful family in Italy during the 1600s, and they were a bunch of mathematicians. Except Jacob was not a mathematician. Does anybody know what Jacob was? Okay, Jacob was a banker. Jacob Bernoulli was a banker. And again, I can never spell Bernoulli. Okay, so I know there's a U in it somewhere. Bernoulli something. Okay. Yeah, B-E-R-N. Okay, N-O-U-L-L-I. N-O-U-L-L-I. And Jacob Bernoulli, okay, he was a banker, but he had a lot of famous mathematician brothers, and his brother moved to Switzerland, and he was a Swiss mathematician, Daniel Bernoulli. Okay, and he was like, Daniel, I'm having this issue, and he says like, well, what's up? He's like, what up, Dan? Okay, so Dan, okay, in the 1600s or like late 1600s, okay, early 1700s, and he says, Jake, what's your deal? He says, I really want to make a lot of money. And Dan, okay, over here, he says, well, I'm a mathematician. I'll help you make a lot of money. And he says, okay, what's your problem, Jacob? And he says, look, okay, if I invest $1 at 5% interest, okay, right, I'm only making $1.05 at the end of the year. And I really want to, kind of screw over the common man, which is pretty much what banks do. And so I don't want to just make my $1.05, right? I want to make more than 5 cents on the dollar. And, is there a way that I could get around, could I say that I'm giving them 5% when really I'm charging more than 5%? Kind of like this little mathematical sleight of hand. And Dan's like, I'm all over that. Absolutely, you can. Let me show you how. He says it's called compound interest. He's like, oh, compound interest, that's interesting. How does that work? And Dan says, hey, let me show you. Let me show you. Let's say that you take your $1 and you invest it at 5%, but you compound this. You divide that interest rate by n intervals, and then you compound the interest over n terms, right? For n intervals, you're going to divide by the n intervals, and then you're going to compound it. And say you do that over 12, a period of 12 times. Do it once a month, which is pretty much what the banks do now. They just do compounding interest, and they give you a dividend every month, or they charge, or you pay them every month as a car payment or a mortgage or whatever, and everything is calculated monthly. Okay, and he's like, well, I'm not satisfied with this. This would come out to be, if I divided this, what would this come out to be? Let's see what this would come out to be. So we're going to go 1 plus 0.05 divided by 12, right? Divided by 12 is that guy. And then I'm going to raise this. I will raise you to the 12th power. Okay, and he's like, bro, look at this. He says, look, you don't just get 1.05 now, right? But what do you get? You get 1.05116. And he's like, well, so what? And he says, I'm still making $1.05, right? And he says, yeah, but Jacob, don't be stupid about this. Okay, you're not just investing $1, you're investing $100,000. He's like, oh, so you're saying that I'm going to end up making $105,116, and I just screwed the people out of extra $5,000? He's like, yeah, bro. He's like, that's how this compound interest thing works. He's like, wait, I have more. He says, what if, but Jacob said, well, why can't we just do this like every second? And he's like, well, that's the beauty of math. We could do this every second. We could compound every second. How about, and Dan's like, how about not every second? How about every millisecond? How about every nanosecond? And he's like, oh, he's like, well, what if we took that $1, right, and we invested at 100%, 100%, right, 100%. We wanted to double our money. Right? We want to double our money. Invested at 100%. These are real high-risk loans. Okay, real high-risk loans, and we're gonna let n go to infinity. We're gonna really mess these people up by going to infinity, whoosh, like that. And so instead of getting $2 at the end of the year, guess what you're gonna get, Jake? I'm like, I don't know, Dan. What am I gonna get? He says you're gonna get $2.71, 8281828459045. And he says, oh my gosh, you're telling me that if I invest $200, I get an extra $71? You're telling me that if I invest if I invest $200,000, I make an extra $71,000 at the end of the year? And he's like, absolutely. He's like, bro, I am all over that. We're going to be rich and rich upon our wildest dreams by doing this, and this comes out to be E, the natural exponent. And this is actually what we call in business and finance, we call this a PERT account. Okay, a PERT account, where this is continually compounded interest. Boom. It's continually compounded interest. If you want to continually compound an interest an account, okay, you ask for a PERT account. It's called a PERT account, P-E-R-T. Okay, PERT account. That's a continuously compounded interest account in business and finance. Okay, again, banks don't normally offer this, okay, because they don't want you to make more money than they do. So they're not going to offer this generally, but what they will is offer you a very, very tiny interest rate that will give you a dividend monthly. So anyway, so does that make sense where this comes into play? It's the natural exponent. It's exponential growth. And it's the limit of this type of compounding interest. Before Jacob Bernoulli was on the scene, we didn't know anything about that. He's the one that invented compound interest. And then Ben Franklin, 100 years later, he said that, what was it? He said something like, the most powerful force in the universe is compound interest. So that's a direct quote from Ben Franklin. You can look that one up. Okay, most powerful force in the universe is compound interest. Okay, so let's look at this compound interest formula. Let's look at just compound interest. Compound interest to begin with. Okay, let's look at compound. Let's look at the formula for compound interest. Okay. Okay, and we're going to go A is equal to P times 1 plus R over N to the NT, right? Okay, that's the compound interest formula where A is the future value. Okay, P is what we call the present value. That's the present value of our money. Okay, R is the annual percentage rate. Sorry, annual. No, that was right. Annual percentage rate. Okay, and N is the number of compounding intervals per year. Intervals per year. Okay, and T is the time in years. Okay, so there's our compound interest formula. Okay, so let's do a little math on this bad boy here, and let's get this into let's see how we can convert this into a PERT account. Okay, into that PERT account. How do we change this guy into the PERT account? Where does that come from? How does the RT where does that being the exponent come from? Well, let's do a little math. Okay, so I'm going to take that formula, and I'm going to say P times 1 plus R over N raised to the NT, right? Wasn't it raised to the NT? But what happens when I raise a power to a power? What do I do with the exponents? When I raise a power to a power, what's the rule? What's the rule when we raise a power to a power? X to the 3 to the 6. What am I going to do?
Multiply?
Multiply. Thank you, Anthony. Okay. Is that Anthony? Showed it.
Yeah.
Okay, good. I flashed Anthony, but then it showed muted. Okay. So X to the 18th, right? Power to a power. And again, we had NT, right? Didn't we have NT? So couldn't I rewrite this as to the nth to the tth power? Is that allowed? Okay, sounds good. Sounds good, sounds good, sounds good. Okay, and so now I'm going to rewrite the R over N in a special way. This equals P times 1 plus 1 over N over R. Are you okay with that? Okay, didn't scare you off. Didn't do anything too scary. Okay, does that make sense? Just take the reciprocal of that and put it down below. Okay, 1 over N over R. Okay, so now we're going to say, well, what? We're going to let X equal N over R. Okay, let X equal N over R, which implies what? That N is equal to XR. Does that make sense? Implies that N is equal to XR. Okay, so P, okay, is equal to 1 plus 1 over X, right? 1 plus 1 over X. Okay, that's N over R is X. Okay, and then what's N? Well, N would have been XR, and then I've got this T on the outside. Okay. Okay, pretty cool. We're getting close. We're getting close. We're getting close. So P is equal to 1 plus 1 over X. Now, again, I'm going to use that same rule of a power to a power, multiply powers, right? So this is 1 plus 1 over X to the X raised to the rth power raised to the T power, but I'm going to say that the power to a power is just a multiplication. So I'm going to let it be R times T. R times T. Write my T better. R times T. And so then we're going to say P is equal to this thing. But what is this thing as X goes to infinity? As my number of compounding intervals goes to infinity, okay, as X goes to infinity, then what's the limit of this thing? That thing just goes to E, right? Then 1 plus 1 over X to the X goes to E. Okay, does that make sense? Okay, cool, cool, cool. And so P, right, P is E to the RT. That's my PERT account. Nice. Boom. Okay. Now you might ask yourself, well, did we do any sleight of hand here with because we started with an n, right? Does that make sense? We started with an n and we left off with an x and then we took the limit. So is there any sleight of hand? And if we look at this step here, okay, and specifically, I'm going to circle that. I'm going to circle this. What is the limit as n goes to infinity? Okay, as n goes to infinity, isn't xr also going to go to infinity? Isn't that the limit, right? Well, let's just say as n goes to infinity, wouldn't xr also go to infinity? Does that make sense? Because it's r is just a constant, it's just a rate, okay? But as n goes to infinity, wouldn't x go to infinity because they're directly proportional? Does that make sense? As n gets bigger, x is going to get bigger, and vice versa. So we started off with n, and we would say, well, the limit as 1 plus 1 over n, right, to the nth power, but that's synonymous to the 1 plus 1 over x because they're going in the same direction. They're both going to positive infinity. Okay, so that's just a little technicality, but I didn't want anybody to say, well, he changed variables, he didn't reconcile the variables. I reconciled the variables, it works, it's good, and what is this going to do? It's going to make a ton of money. Okay, show me the money. Okay, as Jerry Maguire would say, right? Show me the money. Okay, and yeah, so if you want to get rich, just make sure that you're loaning money at an exponential rate, and you'll be very rich, just like Jacob and Dan ended up being in the late 1600s. So there you go. Ended up, okay, owning a lot of Switzerland and Italy. Okay, I am done. Oh, go ahead, Sierra.
No, this is just like the practical application of the proof of the natural exponent as a limit.
Absolutely.
Okay.
Perfect.
Great.
This is the practical
That's just
application.
different,
This is they did this. By the way, they did this before calculus was ever invented. Does it make sense? They just what they did was they hired a bunch of monks to I mean, it was basically around the same time, but Jacob Bernoulli, ran these numbers, okay, before he just did this by hand. He didn't do this, he didn't do this using calculus. Now we can prove this using calculus. Okay. So, other questions?
No, I was just asking if they just discovered the exponential value before everybody, or we used the exponential value to prove what they did.
So they basically what they did, because they were a rich family back then, okay, is they employed monks in a monastery to run calculations. Because what else is a monk going to do all day, right? They're going to pray, and then they're going to do math. So what they did was they hired all of these monks in a monastery. I have a book on this. Oh yeah, it's right here. So the book is, if you ever want to have a really good read or something that will put you to sleep, if you have insomnia, it's right here. It's called the, what is it called? It's upside down. It's called The History of Mathematics. Okay, and it's all these guys. Okay, and it's a wonderful read. And this story is in here. Okay, so it's, again, if you ever have insomnia, you just take this book and you can whack it on your head or something, and then you're out. No, I'm just kidding. You just start reading this thing, and it puts you right to sleep. Right to sleep. Okay, it's better than melatonin. Trust me. Okay, and so again, they hired these monks, these monks to run these calculations. Okay, what happens when I take 1 and divide by 12? Okay, now let's raise that to the 12th power. Let's multiply this out, right? And then it's like, well, what happens if we do it to 100? Now let's multiply that out. Okay, let's do this to 1,000, right? So you have these monks sitting there with pencil and paper writing. Okay, and then they were like, oh, and they were getting a number closer and closer and closer to the natural exponent. They didn't know what it was called, they didn't have a name for it, but they just knew that, oh, this is what happens when you compound interest continually or get very, very close. Because that's what a limit is, right? A limit is we can never get there, but we're going to get really, 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 really close to that value. Does that make sense? So anyway, that's it. That's it for me for today. I will see you guys tomorrow. Okay, if you have any questions, feel free to stick around. Otherwise, I will see you tomorrow.
Thank you, Professor. Have a good one.
You're welcome.
Oh, I have one question. Do I have to, since right now I have the trial, can I work on the trial or I have to pay it today?
I would just make sure that your subscription doesn't end. Okay.
Yeah,
Don't let it go out of. Yeah. So you can use the trial for however long you want. Yeah, you're welcome, everybody. Thank you, Susan. Okay.
Thank you.
Hi, Professor.
Yeah.
I just have sort of like a more, I don't know, personal question about how I feel like in calculus classes, I have like understand the basic concepts, but have trouble with the application. So would the best way to do that to be going through the textbook problems or just like pounding like the WebAssign questions?
Yeah, just the WebAssign I think is good at this point. Chapter 7 doesn't have a whole lot of application. We don't get into that until maybe the next chapter. Just simply because, I mean, we will get into some. I mean, definitely the compound interest, you know, but, you know, we're going to get into a lot of it is theory at the beginning.
Okay.
So
just the WebAssign. Okay. I just wanted to.
Yeah, just the WebAssign for right now.
Thank you.
I mean, I basically cover in the lecture everything that you would see in the text. Does that make sense?
Yeah, okay. Yeah.
So I'm not leaving anything out. I'm just.
Okay, sounds good. Thank you.
Sounds good. Oh, it's the History of Mathematics by Carl B. Boyer. If you ever want to look it up, I can put that in the. It's Carl B. Boyer. Okay. Well, sorry, Carl with an A. Like Carl's Jr. Okay. Okay, see you tomorrow. Thanks. Joseph, are you still here? Yeah. So when you're on Proctorio, they're going to ask you to show your phone and then put that away. And then it's going to kind of lock your browser down. So you won't be able to browse to other sites. You will have the book in your notes as a reference. So does that make sense? Okay, sounds good. So it is open book, it is open note. Okay. Anyone else? Ebony, do you have any questions?
No, Professor, I'm good. I'm just putting everything together.
Oh, Sierra, you don't have to show your surroundings. You just need to make sure that you show your ID and you know, you're good to go. So yeah, you don't have to like rotate or whatever around. That's so, okay. Okay, anything else? That's fine, makes sense. Okay, I'll stop at this point. See you guys tomorrow.